Okay, so the first thing that we need though is that, okay, and then the quick background knowledge, the person that came up with this was Euler. His name was Euler. This guy was like a mathematical badass, kind of revolutionary, arguably one of the most groundbreaking mathematicians in history. But the first thing that we need to look at is a series that was discovered before Euler, which is called Grandi's series, and it was discovered in the early 1700s. And we're going to label this S1. And what S1 is going to be the series of 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever and ever and ever. Okay? And so you look at this series and you say, okay, well, it could be a few things. If you could stop on an odd number, naturally you're going to get 1. If you stop on an even, you're going to get 0, and that's pretty obvious. This goes on forever and ever and ever. But we don't know where we stop. Like I said, this goes on forever and ever. So what this Italian mathematician came up with, he took the average of these two, 1 and 0, and he came up with 1/2. Now I know that's not going to sit right with you guys, so before I go on, I'm going to prove this a little bit further in detail. Okay, so let's look at this series again, S1, and like I said, I know that that explanation of just taking the average of 0 and 1 and setting it equal to 1/2 isn't going to sit right with you guys. So let's take another look at this. So I have 1 minus 1 plus 1 minus 1 plus 1 forever and ever and ever. Okay. So if we look at this, we can start using parentheses. So if we use parentheses, I can set up my parentheses in two different ways. I can set it up like this, and I can set it up 1 minus 1, and like I said, I'm just adding parentheses. I have 1 minus 1 plus 1 minus 1, oops, plus 1 minus 1, and that just comes out to be a whole bunch of zeros added together, which equals 0. Okay, or I could set this S1 equal to, I could set my parentheses over 1 in a very unique way, and that would come out to be 1, and I would have plus -1 plus 1 plus -1 plus 1 plus -1 plus 1 forever and ever and ever. And you can see from here we get 1 plus a whole bunch of zeros, right? Which comes out to just be 1. And that's what we kind of what we said in the very get-go, right? And so we just take the average of these two numbers. So that's one explanation. But then this Grandi mathematician said, okay, but let's look at a more convincing proof. So what if I take 1 minus S1? What would that look like? Okay, well that would be 1 minus all of S1, which is 1 minus 1 plus 1 minus 1 plus 1, so on and so forth. Okay, well from here we get this is equal to 1 minus 1 times 1 is minus 1 minus 1 times, negative times negative 1 comes out to be positive 1, and so this pattern repeats and comes out to be S1. So now we have 1 minus S1 is equal to S1. Well, that's okay, because what's going to happen is we're just going to add S1 to both sides. We're going to get 1 is equal to 2S1. So clearly we can see that S1 is equal to 1/2. And so like I said, this was proved in the early 1700s by Grandi, and so this is what we're going to need for the next part of the proof. So S1 is equal to 1/2, and we see that in a couple of different ways. So moving on, we've proved this S1 is equal to 1/2. So let's kind of let's keep going with this proof. I'm trying to prove this, that S is equal to -1/12, or -1/12. And so I also want to introduce another series, S2, which is equal to 1 minus 2 plus 3 minus 4 plus 5 minus 6, so on and so forth. Okay? So I have this series. Okay? So the next thing I want to do is I want to look at 2s2, or 2 times s2. So I have 2 times s2, which is equal to, and we're going to add these two together. So it's, I have my original s2, 1 minus 2 plus 3 minus 4 plus 5 minus 6, so on. And I'm going to add this s2 to another s2 to give me my 2s2. But I'm going to add it in a very unique way. I'm going to add it by just pushing it, pushing my digits down 1. So I'm going to have 1 minus 2 plus 3 minus 4 plus 5, so on and so forth. And as you can see, I come up with, when I add those two together, my 2s2 is equal to 1 minus 1 plus 1 minus 1 plus 1, so on and so forth. And this is equal to S1, what we saw before. So now we have 2s2 is equal to S1, and we know what S1 equals. S1 equals 1/2. So now I have 2s2 is equal to 1/2. And from here, by simple algebra, we get S2 is equal to 1/4. And so we're going to be using this piece of information. The next thing I want to look at is I want to look at S, which is the series we're trying to prove, minus S2. Okay, that's what I want to look at. And so now I have S, which is 1 plus 2 plus 3 plus 4 plus 5 plus, so on and so forth, minus S2. And so I'm going to have minus S2, which is 1 minus 2 plus 3 minus 4 plus 5, so on and so forth. And from here, you guys are good at math, so you guys know that this comes out to be 0 plus 4 plus 0 plus 8 plus 0 plus 12, so on and so forth. And so we get this 4 plus 8 plus 12, and we go up by increments of 4. We can also rewrite that as 4, and I hope you guys can see this, 4 times 1 plus 2, 4 times 1 plus 2 plus 3 plus 4, which is also equal to just 4s. So now we have something very, very interesting, which is S minus S2 is equal to 4s. And now, but we know what S2 equals. It equals 1/4. So I'm going to just use simple algebra. I have S minus 1/4 is equal to 4s. And once again, I'm going to simplify, subtract by s on both sides. I'm going to get -1/4 is equal to 3s. And then once again, I just divide by 3 on both sides, and I get s is equal to -1/12. And so this is actually used in a lot of string theory, a lot of quantum mechanics, things like that. And like I said, was proved first by Euler, who was a really groundbreaking mathematician. But yeah, so I thought I'd make this video and kind of explain it step by step. Hopefully you guys saw everything and it was very clear. So let me know what you guys think.